going to talk about geometrically what is it that we are doing when you add two complex numbers, or when you subtract a complex number from another complex number, or when you multiply or divide complex numbers. And I think it would be best to take an example. So let's say that we have two complex numbers, z1 and z2, and z1 is the complex number 2 plus j, which is in polar form square root of 5 times e to the j some angle. Let's not worry too much about this at this point. And z2 is 1 plus j times square root of 3, which is 2 times e to the j pi over 3. So if we were to plot these two complex numbers, so z1 lies here, so that's z1. Where does z2 lie? So z2 is 1 units along the real axis and a square root of 3 units along the imaginary axis. So that puts it somewhere over here. So this is z2. And if you were to add these two complex numbers, what you're really doing is you're adding these two vectors, or you're just adding their real parts and you're adding their imaginary parts. So this is pretty much exactly the same as how you would add two vectors. And in this case, you may remember just complete the parallelogram and then add the two and then find the diagonal. So in this case, if you do that, your answer is going to lie somewhere over here. So that vector is going to be given by, so you can see it's going to be 3 units along this axis. So it's somewhere here. So maybe over here. So that's z1 plus z2. Right? Now, how about when you subtract z2 from z1? Well, one way to think about subtracting z2 from z1 is first computing the negative of the vector z2 and then adding the negative of z2 to z1. So if you think about the negative of z2, the negative of z2 is going to lie somewhere here. So it's 1 unit along this direction. So somewhere here. So this is negative z2. And if we were to add z1 and negative z2, the result would lie somewhere in the 4th quadrant. So that's going to lie somewhere here. And you can see we can complete this parallelogram, and then you will see that that's indeed z1 minus z2. Okay. Now, how about if we were to multiply z1 and z2? So when you multiply z1 and z2, it's easier to think of what happens when you multiply them in their polar forms. So one thing you may want to remember is if z1 is r1 times e to the j theta 1, and z2 is r2 times e to the j theta 2, z1 times z2 is r1 times r2 times e to the j theta 1 plus theta 2, right? So if you think about that, what's happening is this. To compute z1 times z2, you can take the magnitude of z1, multiply that by the magnitude of z2, and that becomes the magnitude of z1 times z2. Now the face of z1 times z2, or the angle of z1 times z2, is the sum of the two angles. Now, one way to think about that is to say what z2 is doing to z1 is it's taking z1, it's scaling z1 by the magnitude of z2, and then it's rotating z1 by the angle of z2, right? So that's basically what's happening when you multiply z1 by z2. So in this case, that would correspond to doing something like this. So z1 has a magnitude of square root of 5. z2 has a magnitude of 2. So we are going to take z1, we're going to increase the magnitude, we're going to stretch it out by a factor of 2. So this is going to be 2 times z1. And now we are going to rotate it by 60 degrees, right? Because the angle of z2 is 60 degrees or pi over 3. So you take this vector which has a magnitude of 2 times square root of 5. And then you just go along a circle of radius 2 times square root of 5 until by 60 degrees more. And in this case, you will see that you end up somewhere here. And that is z1 times z2. I think one thing that is very important to realize is when you multiply two complex numbers, that's scaling the vector and rotating it. So in particular, if you are multiplying by a complex number z by e to the j theta, so multiplying a complex number by r times e to the j theta stretches the magnitude out by r, or it may not necessarily be stretching depending on whether r is greater than or less than. It's scaling the magnitude by and rotating the vector or increasing the angle okay. That's it will be useful to build this geometric intuition to what happens when you are multiplying two complex numbers. So how about dividing two complex numbers? So what happens when you have to divide z1 by z2? So maybe z1 divided by z2, we can think of this as z1 being multiplied by 1 over z2. And you can see that if we were to think of them in terms of polar coordinates, so this is r times e to the j theta 1, r1 times e to the j theta 1 divided by r2 times e to the j theta 2. So the new magnitude becomes r1 over r2 times e to the j theta 1 minus theta 2. So in this case, what would that correspond to? So what that would correspond to is taking z1, shrinking the magnitude by a factor of 2, and rotating it clockwise by 60 degrees. Right, so that would put the vector somewhere here. So first we take this vector, we shrink this by a factor of 2 because the magnitude of z2 is 2, and then we rotate 60 degrees. That puts it somewhere here. Well, I don't know whether it's going to be to the right of this vector or to the left of this vector. I invite you to figure this out. So the answer is going to be somewhere here. So the takeaway message from this is that adding and subtracting, you would just do it like normal vector addition and subtraction, but multiplying a complex number by another complex number, scale the magnitude and rotate. Same thing with division, just think of it as multiplying z1 by 1 over z2.